Now the thermodynamics of superconductor. The transition between normal state and superconducting state is thermodynamically reversible. If we decrease the temperature below superconducting transition temperature, material will become superconducting, and if we increase the temperature to above the superconducting transition temperature, material will go back to its normal state. The Gibbs free energy is given by G is equal to U minus Ts minus HM. It's the Gibbs free energy. Let that be relation number 1. According to first law of thermodynamics, dq is equal to du plus dw, or du is equal to dq minus dw. Let that be relation number 2. But we know that dq is equal to tds and dw is equal to pdv. Equation number 3. Therefore, du is equal to tds minus pdv. Let that be relation number 4. See, here P is the pressure applied and dV is the change in volume due to the application of this pressure. In the case of magnetic field, due to the application of magnetizing field, the specimen gets magnetized. Here, due to the application of pressure, the volume of the system changes, and due to the application of magnetizing field, the specimen gets magnetized. So instead of PdV, I can write HdM. It's actually minus HdM because the work is done on the system. Therefore, du is equal to TdS plus HdM, or du minus TdS is equal to HdM. This is relation number 5. Now I differentiate expression 1. It gives dg is equal to equation 1 du minus TdS minus S dt minus HdM minus M dH. But we know that du minus TdS is HdM. So instead of du minus TdS, I can write HdM, that is dg is equal to HdM minus S dt minus HdM minus M dH. Here HdM and HdM gets cancelled. So dg is equal to minus S dt minus M dH. You know, the Gibbs free energy is a constant for isothermal isobaric process. Therefore, if I think the temperature is a constant, then dg is equal to minus M dH. Let that be relation number 6. Now I am integrating that expression, that is integral dg. I am integrating it from 0 to h, that is at a point where there is no magnetizing field to a point where the magnetizing field is maximum, I get is equal to minus integral of 0 to h m dh, or here gh minus g0 is equal to minus integral 0 to h m dh. Here I am taking the superconducting state, so I put a subscript s here. So gh minus g0, gsh minus gs0 is equal to minus integral 0 to h m dh. This is actually the difference in Gibbs free energy of a material in the superconducting state when a magnetizing field is applied and in the absence of magnetizing field. And this difference has a non-zero value only in the application, only in the superconducting state. If we take the normal state, the difference in Gibbs free energy is 0. See, if we take the normal state, Gnh minus Gn0 is equal to 0, because in the normal state, the magnetization inside the material is 0, because in the normal state, most of the conductors are paramagnetic. In the paramagnetic state, the magnetization tends to 0. The magnetization of the material is approximately equal to 0. The magnetization of the material is approximately equal to 0 implies that the magnetic susceptibility of the material is almost equal to 0. The magnetic susceptibility of the material is almost equal to 0. Therefore, the right hand side of this equation, equation 7 becomes 0 in the case of a material in the superconducting state, in the normal state, and Gnh minus Gn0 is equal to 0, or Gnh is equal to Gn0. That is, there is no difference in Gibbs free energy for a material in the normal state when the magnetic field is applied or the magnetic field is not applied. That is, the application of magnetic field is invariant for Gibbs free energy for a material in normal state. We have already discussed that the variation of magnetic field with temperature is very smooth. Here we have the superconducting state, and here we have the normal state. Therefore, the behavior of Gibbs free energy in this normal state is in equilibrium with the behavior of, or the value of Gibbs free energy in the superconducting state. That is, Gn H minus G S H is equal to minus integral M dH. I write this relation because the two states are in equilibrium for critical field and critical temperature. But we know that in the superconducting state, M is equal to minus H. Therefore, Gn H minus Gs H is equal to integral H dH, integral 0 to H dH. This is actually the change in Gibbs free energy for normal state and superconducting state, that is delta G is equal to H square by 2. If we consider the critical field, we can write it is equal to Hc square by 2. Therefore, the change in Gibbs free energy is equal to 1/2 the square of critical field. And we already have dg is equal to minus s dt minus mdh. If I consider a constant magnetic field, this term becomes 0. dH becomes 0 and dg is equal to minus s dt at a constant magnetic field, or s is equal to minus dou g by dou t. Let this be relation number 8. Let this be relation number 9. On considering relations 7, relations 8 and 9. On considering relations 7, 8 and 9, we can write delta S is equal to minus H into dH by dt. But we know that dH by dt is always a negative quantity. Therefore, delta S is always positive. And delta S is always positive implies that the superconducting state is more ordered state. The superconducting state has less entropy than the normal state, because delta S is actually the entropy differences between normal state and superconducting state. The normal state has more entropy and superconducting state has less entropy, which means the superconducting state is of more ordered state. Specific heat capacity of superconductors. Specific heat. See, if we plot a graph with temperature along x-axis and specific heat capacity, along y-axis, for higher temperature the variation is almost linear, and when it reaches critical temperature there is a sharp increase in superconductivity, then thereafter it gradually decreases to 0. Gradually decreases. This sharp increase occurs at critical temperature. The sharp increase at this point, at the critical temperature, suggests the existence of an energy gap inside the superconductor. The specific heat capacity in normal metals is due to two factors, that is C is equal to C lattice, that is the contribution of lattice to the specific capacity plus the contribution of electrons, C electrons. This is the case of normal metals, Cn, normal metals. But in the case of superconductors also, C superconductors, specific heat of superconductors is equal to Cs lattice plus C S electrons. But the contribution of lattice specific heat for the two phases, normal phase and superconducting phase, is same. Therefore, The difference in specific capacity in the superconducting state and the normal state is due to the contribution of electrons, and the electronic contribution of specific heat is found to obey the relation C electronic is equal to A e raised to minus delta by kT. Here A is a constant and this delta is the energy gap. This energy gap occurs inside the material just above the Fermi level. See, in the normal case of electrons are filled at absolute zero below the Fermi level, but in the superconducting state there occurs a small energy gap in this region, and the small energy gap is denoted by Eg. If we take the density of states, we have Z of E, which is the density of state, and the variation is like this for a normal metal. Here we can take temperature, either temperature, or we can take energy as a function of temperature. But for superconductors, the variation is like this. Density of states here, and here we have a sharp variation energy gap. Thereafter it varies. There is a small energy gap we can found here. Here also it is temperature or energy as a function of temperature. This energy gap can be explained on the basis of several theories, and several theories have been developed so far to explain the phenomenon of superconductivity. You should understand one thing, that superconductivity is still an open subject. This is not a closed one. So many theories are being developed and so many theories are being developed to explain superconductivity satisfactorily, but no such theories have been found to explain it completely. But one such very efficient theory developed to explain superconductivity is the BCS theory. BCS theory was successful in explaining most of the experimental facts that we observe in superconductivity, like Meissner effect and thermodynamics of superconductor, like London penetration depth, etc. We will discuss here only the main aspects of BCS theory, and the theory is developed by Bardeen, Cooper and Schrieffer. Bardeen, Cooper and Schrieffer developed the BCS theory. This is actually a microscopic theory which was very successful in explaining the macroscopic quantum phenomenon behind the superconductivity. So it is also called the microscopic theory of superconductivity. The main aspects of superconductivity are: one, the lattice electron interaction via lattice. Electron interaction via lattice. 2, Cooper pairs. 3, BCS ground state. Here we can look all these aspects one by one. First, the electron interaction via lattice. We know inside the metals, the electrons flow through the sea of positive ions. Positive ions, these are all positive ions, and electrons move through this positive ion. We can consider one such positive ion here. And due to this electron, the positive ions are attracted towards this negative electron, and this electrostatic attraction causes a lattice deformation, and as a result, another electron in the neighboring region see this deformed lattice, this distorted lattice, and the electron is being screened by all these positive charges surrounding this electron. Therefore, this electron in the neighboring region sees a resultant positive charge and gets attracted towards this deformed lattice, and these two electrons get coupled together and move together, and due to this movement, due to the simultaneous motion of these two electrons, the resultant current gets increased, and the coupling takes place here not only for these two electrons but also for all the other pairs of electrons inside this crystal lattice exactly through this same method. And see, if in terms of quantum field theory, see, let this be the k vector associated with the one electron. I can denote it by k1. This electron emits a phonon which is captured by another member here, let it be q, and this electron moves after leaving the phonon, and the associated k vector is denoted by k1 dash. So I can write an equation here that k1 k1 minus q is equal to k1 dash. Now, what will the other member do? The other member absorbs this phonon, virtual phonon, and let that member be moving with a wave vector k2. On absorbing this virtual phonon, the wave vector changes to k2 dash. So I can write k2 on absorbing q changes to k2 dash. So therefore k2 plus q is equal to k2 dash. On adding these two equations, we get k1 plus k2 is equal to k1 dash plus k2 dash. So the wave vector is also found to be conserved here. So this is the electron-electron interaction via lattice. Here I explained the electron-electron interaction via lattice on the basis of classical theory. Here I explained the electron-electron interaction using quantum field theory. The second aspect is Cooper pair. We know electrons are fermions. The Fermi-Dirac distribution says that if E is equal to 1 by exponential E minus EF divided by KT plus 1. This is the Fermi-Dirac distribution law. And at absolute zero, all the electrons inside a system occupies the ground state, and here we assume that the ground state is completely filled. and the ground state and since the ground state is completely filled, the momentum distribution assumes a spherical shape and is also called Fermi sphere. The momentum distribution along the three axes is represented as kx, ky and kz, and the momentum distribution has a spherical shape and is called Fermi sphere, and at absolute zero all the electrons will be inside this sphere. We know that P square is equal to 2me, let that be relation number 1, where E is kinetic energy and P is momentum. We also know that P is equal to h cross k, or P square is equal to h cross k square. Equation number 2. Left hand sides of equation 1 and 2 are same, therefore right hand sides can be equated. Therefore h cross square k square is equal to 2me, or we can write k square is equal to 2me divided by h cross square, or k is equal to 2me divided by h cross square, the whole raised to 1 by 2. See, all the states are completely occupied. So what will happen if we add one more electron to the system at absolute zero? What will happen if we add one more electrons to this system at T is equal to 2 Kelvin? According to Pauli's exclusion principle, one more electron cannot be added into the system. What will happen if I add two more electrons to the system? The two more electrons cannot be occupied inside this Fermi sphere. So they will be forced to occupy a level whose energy is greater than the Fermi energy. So if those two electrons, if they are with opposite spin, that is one electron with spin up and if another electron is with spin down, these two electrons get coupled each other and they occupy a state. Due to this coupling, the energy of the system will be minimized, and now they can go into the region where the Fermi energy is very less. And as a result, they can contribute to super electric current. And if such pairing is possible for one pair of electrons, that is, such pairing is possible for two electrons, all the other couples inside the material satisfying this condition can be paired, or more Cooper pairs can be formed, and they can also contribute to electric current. Now the third one. The third one is BCS ground state. In normal metals, electrons lie below the Fermi level at absolute zero, and even a small excitation energy can take the metals to the conduction band, and they can contribute to electric current. But in the case of superconductors, if we give some excitation energy to the electrons lying in the Fermi level, they get excited, and not only excitation takes place here, but also coupling with another electron takes place, and as a result the total energy gets reduced, and an energy equal to that binding energy is to be supplied to break that coupling, and this coupling energy will be more if the electrons take place in coupling are of opposite spin. So these electrons in the coupled state lying along the Fermi level can contribute, or along the Fermi level or just below the Fermi level can contribute to electric current. Josephson effect. So we consider two normal metals and a small insulator is placed between the metals. The thickness of the insulator is very low. It is of the order of 10 angstrom or 20 angstrom. And if I apply a potential difference, electric current can pass through the junction. It's actually a quantum mechanical phenomenon, very similar to quantum mechanical tunneling. And this electric current and the voltage applied here obeys Ohm's law, which means the graph is a straight line passing the origin, and as voltage increases, the current also increases. These are two normal metals. This is a normal metal and this is also a normal metal. But when we replace this normal metal with a superconducting metal, we replace one of the normal metals with a superconducting metal. See, let this be the superconducting metal or superconductor. The flow of electric current will not take place until the value of potential V is equal to delta by 2E. That is, if I plot a graph for this one, the variation will be like this. The current will start to conduct only from this point. Here is the voltage, and on the y-axis we can take current, and current will start to flow from this point where the voltage is given by V is equal to delta by 2E, because that much energy is needed to take the electron to the conduction level, to the excitation level. And now we can replace these two metals with a superconductor. When we connect two superconductors with an insulating layer between the two superconductors, and electric current will flow even if no potential difference is applied. These two are superconductors. This is a superconductor. This is also a superconductor. And there will be a current even if no potential difference is applied, and the current is given by I is equal to I0 sin phi or cos phi, sin phi or cos phi. And if we plot a graph with voltage along x-axis and current along y-axis, we get this type of thing. See, here the current starts even when potential is 0, even when the applied external potential is 0, and as applied external potential increases, current also increases. Now what will happen if an additional static potential difference is applied to the system? If an additional potential difference is applied to the system, it gets an additional phase change which is given by delta phi is equal to Et divided by H cross. Therefore, in that case, the resultant current is given by I is equal to I0 into sin phi plus an additional phase change delta phi, or I is equal to I0 into sine phi plus Et divided by h cross. And from this expression we can see that when a static potential difference V is applied to the system, an additional phase change occurred, and we can write 2 here because 2 electrons are paired here. And when we compare this equation with our normal component, normal expression for current, I is equal to I0 into sine phi plus omega t, we get the frequency of this current is given by omega is equal to 2E divided by h cross. This is called AC Josephson effect.